And now I pass it on to Douglas, who doesn't need any introduction, who is going to talk about more seriously about water and forest.
So thanks very much for the invitation. Oh, wait. Okay, we go. So an optimist guide. Oh, here we go. I'll wait for the presentation to go up. So I called it an optimist guide because a lot of these talks are often quite depressing about how the world is getting difficult and hot and hard. But my real message today is we can actually fix this. And trees and forests are a big part of fixing it. So this is really key to a lot of what CIFOR-ICRAF are potentially doing. And I put in 3 propositions here. That everybody cares about reliable water. I think a lot of people here probably talk about carbon, but it's very hard to persuade many people in remote parts of the world that carbon matters. Everybody cares about water. The real talk today will be explaining why I think trees offer transformative gains for reliable water. And I think the premise here is that if we can actually fix water, we can also make a major contribution to fixing a lot of other things. Without water, we can't. So water is really fundamental. So a little bit of the outline. I'll talk a bit about why this is important. I think it's kind of obvious. It's a topic where there's a lot of misconceptions, so I just want to highlight that particularly. Then talk a little bit about infiltration and groundwater, touch on atmospheric processes. Anastassia, who will talk after me, will talk more about the atmospheric side. And then briefly about needs and opportunities. So if you look at statistics, there's various estimates, but the majority of the people on the planet suffer from some kind of water scarcity. I think people who suffer year-round, it's around 500 million is the current estimates. And the situation is not getting better. Populations are growing, water availability is declining. So there are depressing statistics here. This causes hardship, it causes many other problems, it causes problems for the environment. And if you look at the actual people who've tried to make a study of it, the less water we have, the more conflict we have. We also have huge numbers of people moving from certain regions of the planet to other regions, causing major problems. Water is not just about water itself, but it's also about the service it provides in terms of cooling. So this is just to point out that about half of the sun's energy that lands on the Earth's surface goes into evaporating water. If that water isn't there, it goes into heat instead. So it's also key to just temperatures. And I won't have time to talk so much about clouds, etc., but there's other processes here as well. Just a couple of recent studies to talk about. One was earlier this year saying how the world is getting drier. I can't really point for the audience in Nairobi, but on the top here, you see a figure, global soil moisture. And the authors of this article, Sheil et al., told us that there was this global change in soil moisture over the last 20 years or so, equivalent to a loss of about a little bit more than 2 centimeters of water across the Earth's surface. Soil is getting drier. On a map up there on the top right-hand corner, you see it's not evenly distributed, but it is quite severe in Central Africa. The authors of this article talk about it in terms of normal kind of climate change and getting warmer. Then the lower study, also in Science earlier this year, is talking about less low cloud cover and how this is responsible for a lot of the increasing temperature of the planet. Again, the authors here talk about it in terms of a normal climate change narrative. But both these problems could also be interpreted as being about water. But neither of these sets of authors of these 2 articles talk about land cover. Neither mention forests as an issue. For me, I think this is a huge error. So we know that trees have many benefits. I guess people in this room, I don't have to tell you, it's kind of obvious. Water is the controversial one, so we'll jump straight to that. There is quite a history here, and I'm just pointing out a book that I just read recently, Bonan's book. It's a thick book, and it looks at the history of how we viewed water and climate in general. And it goes right the way back to the time of the Romans when they were writing about springs drying up when forests were cut. We talk about Columbus's voyages where he actually recognized that the islands in the Atlantic, Canaries, Azores, and Madeira had a declining rainfall when the forests were gone. So people have been talking about these things for a long time. He doesn't go so much into the local knowledge, but there's plenty of that too. And I think what's really striking when you see this book is there's a lot of very black and white opinions. Forests are good or forests are bad. There's very little in the middle. There's very little nuance. Plenty of disagreements. Exciting stuff. So I like to draw on this example because it was kind of a high profile one back in 2005. I was working in CIFOR at the time, so I think some of you will remember when this article came out. And there was this article in The Economist called Down with Trees. Okay, this looks scary, right? If you're trying to be pro-trees, big article, down with trees. Planting trees can exacerbate drought and fail to tackle climate change. And it was actually addressing an article published in Science with a lot of fanfare showing that areas where we compared without forests and with forest afforestation, 506 comparisons, pretty impressive. In general, we were seeing quite a big decline of water coming off these landscapes. Quite a big shift, and particularly severe in the drier areas. What you didn't see in the publicity that most of these forests, these afforestation projects, were monocultures of exotics growing in dry sites that probably shouldn't have forests in the first place. Only 2 of them were in the tropics. None of them were in the dryland tropics. No open forest. But I think for many people reading this, they thought, well, this is the final word. This is 506 comparisons. Forests are bad, right? Totally misleading. We already knew that there are big parts of the tropics where forests are actually providing an awful lot of water locally. So this is just a nice picture here of where, sorry, I have to give you the scale, don't I? So the bottom maps here are the different parts of the tropics where the different colors show the amount of water that's actually captured from droplets. So not from rainfall, but from droplets, from clouds, from mist that particularly is flying into many mountain forests of the world, contributing a lot to the water. There are some particularly high values. What's it, 1990 millimeters per year in some cases. In some specific cases, even 3/4 of the water that's captured by those forests. I mean, these are very specific, exceptional cases, these high values. But the point is, this is common in many mountain regions of the world, where a lot of the water that is captured by the forest is not rainfall, but droplets from cloud. We kind of already knew this, but somehow it was forgotten. But these forests are obviously super important, and they're super important for the water they provide. So there are good forests out there. The idea that none of the forests are good is still widely found. So I just like to quote this article in 2022. You see the citation at the top, Marshall et al., and it includes hydrologists. That amongst the authors were hydrologists who should know better. And they talk about the misconceptions that trees can be good for hydrology, can be good for water production. These misconceptions frequently find their way into public discourse and policy, most notably that restoring forests lead to an increase in stream flow. So in their minds, forests are, I guess, still never good, though we know that's wrong. So they call that misconceptions, and I guess one of the people that they're looking at is people like me who think it's not a misconception. But we have many examples where there are quite good studies saying where actually afforestation brings better water to a catchment. This is from a study that we're putting together, a compilation. There are some good examples. Partly these studies are confusing the idea of what the water is coming from a catchment in terms of total water and useful water. There's a concept here, base flow, that hydrologists talk about the actual water that's available, particularly in the dry season, versus the water that runs off a landscape quickly and can be quite destructive. So that's one of the things that's confused. Also, if we look around the world and actually make a prediction as where across the different continents, we would actually get a benefit as opposed to a cost from keeping as opposed to losing forests, you actually see that there are quite a number of places where actually you get a decline in water availability if you lose forests. It's a slightly complicated figure. I'm trying to think whether I explain it or not, but the colors here along the bottom show you, particularly to this dark blue, where you get a longer period of strong base flow from the catchment if you have maintained tree cover in this catchment. Okay, so the summary of this is that about 20% of this landscape, this region, sorry, you would actually get quite clear benefits in terms of month or more of additional base flow. And we've done a similar study recently for areas that are being restored, and it's about the same, that about at least 20% of sites, it wouldn't just be constant, but it would be an increase. So this summary and the one that we've done recently neglects partial tree cover, and it assumes that rainfall stays the same. These are important because we'll come back to them. So this was a study I wanted to talk about briefly, so I'm jumping around a bit. Some years ago in Burkina Faso, published in 2016. I think, Daniel, you were an author on this. Looking at the idea that partial tree cover is also something to consider, and I won't go into all the details of the study, but several years of data collection in an agroforestry landscape in Burkina Faso, landscape where there were hoofed animals working across the soil surface. It was to some degree compacted. You can see the rainfall in the top picture there. Often falls in quite hard periods of a lot of rain. A lot of it is runoff and lost. And this is a landscape where there isn't very much rain, and people are trying to live from water they draw from wells, I think. And what we see here, this is the graph. I shouldn't point at it because nobody can see, right? So along the bottom here, you have relative canopy cover, and on the y-axis, groundwater recharge in millimeters per year. And the point you should look at, I think the animation shows here, if we have 0 tree cover, we expect the recharge to only be about 10 millimeters per year. But if we have the optimal tree cover, which is up here around 40% canopy cover, we can actually multiply that several times. It is a model result, so there are assumptions in here. I don't want to pretend otherwise. But the point is we do actually see that some tree cover is better than none, even if maximum tree cover would also be negative. I think it's also worth pointing out it's quite a broad peak, so you can get the benefits across quite a range of densities. I also wanted to highlight that CIFOR-ICRAF has great data sets for actually exploring these kind of things, because that last study was in one site. How general is that? And you have data, which I think is super valuable for actually looking at these kinds of things. So one of the variables that's key here is the infiltratability. It's a difficult word to say. Is that correct? I'm looking to see if people look approving. Infiltratability of the soil. It's quite a technical thing to do, but you have great data sets across Africa. And this was just published, I think, last year, looking at the infiltration properties of the different soils. So we can actually start to look at the kind of information we would need to actually talk about what would optimal tree cover look like across these landscapes for water recharge, if that was the goal of the land cover. Okay, I want to jump now to rainfall. Highlight that rainfall is a key attribute of maintaining a good livelihood across the world. It needs to be reliable. It's not just the amounts, but the reliability of it. Most deaths in natural disasters still relate to water. Problems of floods, problems of droughts are huge worldwide. Probably pretty obvious, right? We are in a world where we have amazing data. This is a figure at the top that I just downloaded last week when I was writing the presentation. You can get this even today, I guess, and update it. But we can see precipitable water, the water that's available for rain in this upper figure, and we show how it moves around the globe. So we have these amazing data sets going back decades and decades. So we start to have a pretty good idea of how rainfall works, where it comes from and where it goes to. And I'd just like to summarize in the bottom table that we know how much rain falls on land. We know how much of that comes from the ocean and how much of it comes from the land surface. The idea that water that comes off the land surface can fall again on the land surface. And I think what's surprising for a lot of the people I tell this to is the majority comes from the land surface. Not if you live in a country like I'm from Ireland, most of our rain comes from the ocean. But in huge parts of the planet, most of your rain comes from the land surface. It depends where you are. And this is kind of a famous figure, but I like to put it up because it really makes the point that it depends where you are. The top figure is showing you the ratios of the water that's coming off the land surface that is falling back on the land surface. So we see on the right-hand scale, up in the red and up to the black, it's going up to 100% there. You see that there's large parts of Northern South America, Central Africa, and parts of Central Asia, where a lot of the water that's coming off that landscape is falling again on the landscape somewhere else, perhaps. And in the bottom figure, it's the same scale, but asking how much of that water is coming off the landscape that's falling locally as rainfall. So if you look here, you can see that there's big populations, I guess, I have circles here to highlight it, areas with large human populations where a lot of the rain is coming from rain that comes off landscape somewhere. It doesn't say where, but we do have data. This is just a summary data. But the point is there's huge amounts of rain, huge amounts of people depending on this recycled rain. It's not a small thing. If you're a farmer in China, your rain is probably coming from Central Asia, from Europe. If you're a farmer in West Africa, a lot of your rain is falling, having already been falling on the land somewhere else. So you might think if there is an effect of the landscape on that rainfall, you'd want to know about it. So we tend to look to climate models to kind of answer questions about rainfall. This, I guess, for most people, this is where we assume that all the science goes, at least in the climate models, into making the best predictions we can. And we have increasingly sophisticated models, global circulation models, Earth system models, to actually look at how the climate will change with land cover. There's been a lot of work on trying to represent this. I'm not going to go into it all. That's not really the point. The point is it is becoming more and more sophisticated. But there are still major uncertainties, particularly in cloud cover, particularly in rainfall. I like to cite the authors who actually write ICPP reports, just because it's not me criticizing, but there was this nice study in Science in 2013, What Are Climate Models Missing? And they explain that rainfall over land is largely determined by unresolved processes. This is the main limitation in current representations of the climate system. So they're telling us that their simulation models don't work particularly well. So they're not hiding this. They're happy to tell you. And in the last report from the IPCC, just looking at what the authors said in 2021, they say there's little improvement for rainfall, for the summer monsoons, the diurnal cycle, the frequency of rainfall. So we still have big problems in actually predicting rainfall patterns in the models. The models don't work very well. I think when I say this often to students, they kind of look at you like you're a climate change denier. But this is the authors of the people who make the models who actually do the predictions of climate change. It's not me, it's them. To highlight things that we know quite well is that generally when we have less forest, we have less rain. So this is just to highlight a study that I was involved with a few years ago when we looked at rainfall across Borneo, across Kalimantan, looking particularly from the early 1970s to 2010. We saw quite a marked decline in rainfall, about 20% decline. The biggest decline was where most of the forest cover was lost. So this isn't about mechanisms, it's just empirical data. This was from rainfall data from these locations. And I think since we published that, there's been quite a number of other studies in different parts of the world, in the Amazon, in Africa, even in Europe, and a nice trans-tropical study by Smith et al. Basically, everybody's telling us that when we lose forests, we lose rainfall, particularly at large scales. At local scales, there can be some noise here. You can actually get local effects where you get maybe an increase in one place rather than another. But in general, overall, rainfall seems to decline. And I think it's also quite telling in the Smith et al. Article when they actually look at this reanalysis data. This is data that's worked through with models. They also don't see it, but when they look at actual rainfall data, they see it. So again, the models are not actually capturing what we want them to capture. Okay, a couple of recent insights that I think are important to highlight. That trees are actually the main source of this recycled rain. I think way back in 2013 or so, people would have said it's about 20 to 30% of the water that's being re-evaporated to the atmosphere is coming from vegetation. But that estimate has gone up a lot. It's about 3 times that. So if you thought it was important then, it's 3 times more important now. So that's an important insight. I think the other thing that there's really been a lot of work on recently is this idea of non-linear relationships, the idea that a small difference can make a big change. And this is something that, again, the models are not very good at capturing. But there's this idea of triggering convergence, triggering the water to actually condense. This process, the water doesn't condense in the atmosphere until it reaches a threshold. But once you reach that threshold, things change. Okay, so I won't get too much into it. There's a lot of work on this tipping points, but I think this is something so profoundly important, it's hard to ignore it. If we talk about tipping points, it's the idea that a wet region can suddenly become dry. It's also an opportunity to take a dry region and make it wet again. It's maybe not as hard as you think. So why are trees special? There's a number of different things that we've talked about. We talked briefly about cloud capture and infiltration, talking a little bit about recycling here. I think Anastassia after will talk a bit about some of the other relationships, but there's many others. I'm just trying to give you a summary of why I think this stuff is super important, but there's many other things we could have talked about. So the overall conclusions are the effective tree cover. It shapes the magnitude and reliability of water availability. It depends a lot on context. There are powerful feedbacks at play. Forest losses can be catastrophic, but there's also the opportunity, which I haven't really gotten into today, but you'll have to take my word for it. It can be transforming. We can reverse these things. The thresholds can actually work in the other way. We can actually bring water back. So there's huge opportunities here. I briefly outlined what I thought was the research agenda. These were just examples, but I see that there's a difference areas we can talk about: the land process, the atmospheric processes, the different options and trade-offs that we have to deal with, trying to build these models so that we can actually synthesize these different things and get a proper vision of how the world could be in the future. And then there's all the policy and governance issues. The idea of water cycle as a common good, ensuring equitable access to reliable water, and the issues of development if you don't have reliable water, I guess. So there's a lot of implications here. I think a lot of this is stuff that CIFOR-ICRAF has expertise in. I don't think any one group anywhere has expertise in everything, but I think if you look at this, you'll be surprised how strong you are, we are, on these topics. So going back to my premise, everybody cares about reliable water. Trees offer transformative gains for reliable water. And if we actually fix this, we can also fix a lot of other stuff. Let's try it.
Thank you, Doug. Our next speaker is someone who is probably a bit less familiar for you. Anastassia Makarieva is online from St. Petersburg. She works on, I have to read it again, I mean, it's not the Theoretical Physics Division in the Petersburg Institute. And she's the brain behind the concept of biotic pumps. And she was going to present us something that are probably a game eye-opener for a lot of us. So Anastassia, welcome. Thank you for joining us. And do you have 20 minutes? You can share your presentation.
Okay, just a moment. Is it okay?
Yeah, it's okay. We'll see and hear you.
Okay. Okay, so first of all, I must say that it is a great honor for me to speak at this conference and to share my views with people who I know deeply acknowledge the existential importance of forests. And we are meeting at a time when not only the global mean surface temperature has reached a new high, but also the rate of the warming has been rapidly increasing. So while Douglas was talking about water availability and regional perspectives on how important water it is for everybody, I will provide a more global perspective of how forests and water could be relevant in this global context of increasing emergency, I would say. What is essential about current situation in climate is that not only the rate of warming has been increasing, and on this graph to the right, you can see the rate, how the Earth's energy imbalance, so the heating rate is increasing recently. It has doubled in recent decades. But also what is important, that climate models are not able to describe it. So they are failing to describe this crucial process. And then we can think, why do we need to refocus on forests and water? Why are we having this session today? Cool, forests beyond water, beyond carbon. This is a recognition, from my perspective, of two things. First, that so far we've been focusing on carbon. And second, that we have overlooked something very essential. And our long-term focus on carbon reflected this guidance from global climate models that have for many years represented the main tool of how we understand climate. And these models unambiguously tell us that forest impacts on climate are negligible if we are talking about anything beyond carbon. You can see here a figure from a major report, and these yellow marks indicate the impact of non-carbon forest impact to global temperature change. It is like about few percent of what's really going on. So, if the models were doing fine describing climate, and they were telling us that forests don't matter except as like stores of carbon, we could hardly argue for a greater role, for focusing more on water and its role in climate. But they are not doing fine. Like Douglas mentioned a few controversies, but what I want to show you here is a compilation of how different global climate models predict response to deforestation in terms of how much of water vapor will be transported from the ocean. And you can see that not only the magnitude of the response differs by more than an order of magnitude across models, but even the sign is not predicted. So we can't know from models what happens to the water cycle if we deforest land. They don't provide any guidance. There is no robust response. Accordingly, there is a growing recognition in the scientific community that models alone may not be a trusted source of information and guidance concerning the climate. And here you can see quotes from high-profile scientists who draw attention to the fact that our understanding of what's going on, of the key processes behind climate change, lag behind formal numerical modeling. So we're at the point of reprioritizing understanding from first principles supported by empirical evidence. And analysis of multidisciplinary evidence requires clear theoretical concepts and thinking frameworks. So, from my perspective, one of such unifying concepts would be the idea of natural ecosystems, forests primarily, forests, which are the most productive ecosystems, serving as climate stabilizers, and their loss in the course of land use and land cover change, as well as in the course of oceanic exploitation, if we talk about ecosystems of the ocean, has become a major driver of climate destabilization. And here we are talking not just about global warming, but about destabilization in the broader sense, including the increasing frequency of droughts, floods, and other water-related cataclysms and long-term trends like soil moisture loss. So let me show very schematically how the forest can enter the current vision of global warming. So this is the hardcore physics part of my talk, so please bear for me for a moment. It will be just a few minutes. So in this graph to the right, you can see how air temperature depends on height in the atmosphere of the Earth. And in the steady state, the Earth receives as much energy from the sun as it releases back to space. And this heat released from the Earth to space comes from the upper radiating layer, which you can think of as where the greenhouse gases molecules sit, those who radiate directly to space. So they radiate more directly to space, and nobody catches this radiation, and nobody resends it back to the Earth. And the higher the temperature of this layer, the more heat it will release. So when we add more greenhouse substances, this layer goes up, and then there is as once again it goes up and becomes colder. So at this point, the Earth releases less energy than it receives, and it begins to warm. And this warming goes to the surface through this line, which is the how temperature declines with height. So the slope of this line shows how fast the temperature declines with height. And so we have warming, and such that the temperature of this upper radiative layer becomes again equal to the equilibrium temperature. So this is the classical conventional view of the greenhouse effect, which captures the increasing CO2. Now going to the central scheme, we have clouds and transpiration. What do clouds do? Clouds reflect more sunlight, so they change the equilibrium temperature of this upper layer. So even if we don't change the height of this layer from which the radiation goes to space, still we can change the surface temperature by reflecting more sunlight. And if there are forests and they're making clouds, then the temperature on the Earth's surface is cooler, lower, and if we remove forests and remove clouds, there is more sunlight absorbed, and there is warming. So one thing is clouds. Second thing, you can see from the geometry that we can not only move this line, the gray one, not only move the blue one, but we can also move the red line, which is how the temperature changes with height. When there is transpiration, forests capture a certain part of solar energy at the surface as what is called latent heat. And this latent heat is then released higher in the troposphere and goes more unimpeded to space. So by transpiration, the forests smooth the temperature lapse rate and thus cause cooling, relative cooling. If we reduce transpiration, then more heat remains at the surface and the lapse rate becomes steeper and we have warming. So both effects will be global, and both effects will involve how forests handle water. So now let me show that both effects are very real and significant. If we are looking first at clouds, we have evidence that the record heat in 2003 could have been facilitated by a biospheric breakdown, because we know that in this year the Amazon suffered an unprecedented drought, and there were also unprecedented fires in Canada. And in both cases, transpiration and cloud formation were drastically reduced. We can see that cloud cover was reduced over the Amazon and the adjacent forest, adjacent oceanic regions, and there is also a hotspot of cloud reduction in over Canada. And this is backed up by our knowledge of how efficient forests are in generating low-level clouds that cool the Earth. We can see here on the right graph that the more productive forests are, the more efficient they are in generating clouds, while when we change them for less for non-forest systems, the generation of cloud cover is drastically reduced. Now, regarding transpiration and the role of atmospheric moisture transport. Here again, we can see that heat captured as latent heat through transpiration at the surface goes up to the atmosphere and is released to space from the upper atmosphere. But this process does take time. So if there is a long-range regular flow of moist air from the ocean to land and back through the upper atmosphere, this heat has time to be released and thus cools the Earth. If we deforest and disrupt this long-range moisture transport, we can see, as Douglas also mentioned, we can see, and this is what we find in observations, that there will be more rigorous precipitation over the deforested areas locally, and these more rigorous air motions will be so rapid that the heat will return to the surface, and so this will cause an increase in temperature lapse rate and warming. And as we showed in a recent study, indeed, the models don't capture this effect. And indeed, the trend in lapse rate is unexplained and is very significant. So especially over land. So there are strong lines of evidence that when we deforest and when we disrupt the moisture flows associated with transpiration and energy flows, this produces a globally significant effects. So from these more specific examples, I want to drawing closer to the conclusions and more general concepts. Generally, for these climate regulating processes, forests require water, and the capacity of forests to manage its water balance naturally declines when we begin to disturb it, to log, to burn, or to disturb in some other ways. And so this leads to climate destabilization through disruption in the water cycle, which can be incorporated using the notion of climate sensitivity. Climate sensitivity is how much the planet warms is CO2 doubles. So just it is can be calculated from models, and the models differ greatly in these estimates. So in the current narrative, like if we think this will be the simpler part without formula or anything, like if this guy is CO2 and this is Earth and this is warming, so the more CO2, more warming. This is what is the current narrative. If we include the ecosystems and incorporate the biosphere, we will see that there are different situations in which it is more difficult for a given amount of CO2 to warm the planet, or less difficult. So if we destroy forests and remove their climate regulating potential, so we will get more warming and more climate extremes with the same CO2. So, and if in the current narrative, we focus on decarbonization and biodiversity and everything, and forests are a minor thing, which we only consider with like something of secondary importance. Then if we incorporate the biosphere, it is a key component of our strategy, how we even think about what's happening to the planet. So we need to preserve, along with all our measures, all our other measures that we consider, we need to preserve ecosystems to decrease climate sensitivity to CO2 accumulation. So more forests, functional forests, self-regenerating forests we have, the more stable our planet is and its climate. So, and conversely, the more we take from the ecosystem, and the fewer resources it has to buffer climate extremes. And so if we saw this 2023 anomaly after a drought in the Amazon forest that was plundered, especially during Bolsonaro times, with increasing deforestation, then now if we have this large-scale deforestation project in Indonesia, we are asking for more global problems. And what is ironical, that these terrible developments are facilitated by carbon-focused narratives, because from what I know, much of the argumentation behind this deforestation project in Indonesia is that they will have a green fuel, like a renewable fuel. But this this will actually destabilize our planet even further. So conclusions would be that it so happened that evidence that we have now shows that climate science is in need of conceptual rethinking, and there is a rare opportunity that its trajectory moves towards recognizing a greater role of the biosphere. And we need to know this how imperfect the models are, and not be afraid of bringing evidence from different fields of knowledge, which people working on the ground often get, and talking about it, because the models are currently failing very spectacularly. So natural forests buffer the climate by regulating atmospheric humidity, moisture transport, and cloud formation. And it is absolutely crucial to stand up scientifically against large-scale deforestation projects. Because, and it is one thing I also want to mention, if we don't raise the importance of forests in the global climate agenda, we can't hope that any funding that currently goes to climate issues will go to the forests. So it is also very important, if we demonstrate that forests are crucial players, this may totally change the flows of funds towards their preservation or restoration or whatever. Currently, the pictures that I showed in the very beginning, that they are not contributing anything except being carbon storage, is depriving the forest water topic of significant funding. Meanwhile, environmental stability provided by natural forests will support long-term economic planning and protect investments, especially in the long term. And so I think that international and interdisciplinary collaboration needs some clear concepts, some unifying ideas. So probably forests as climate stabilizers could be one. Thank you very much, and you can download the presentation following this address. Thank you.
Thank you, Anastassia. Thank you very much. And then in case you are not convinced, forest matters, and it is not said by an old forester, it's said by a theoretical physicist. So now we are going to move to